gravity. Okay, so this law of gravitation, it came around the 1600s. Okay, and it was a very profound and significant uh, discovery that Newton came upon. Okay, and to just think of the perspective, right? He was just 30 years old. Okay, and he had some scientific basis to formulate this law of gravitation. Okay, Newton was quite prolific as a scientist. He did a lot of work, as you already are familiar with his three laws of motion. Okay, he also co-invented calculus. Okay, with Leibniz. All right, so there was a huge tussle for about 100 years until Leibniz died as to who actually invented calculus as well. Okay, and you might be reading about calculus now, where you take limits, differentiation, and all those stuff. And Newton came upon the idea when he was working with his laws. Okay, so of course Newton became much more famous for his law of gravitation during the early 1700s. Okay, and his prediction of the orbits that were in elliptical trajectory around the sun was in excellent agreement with Johannes Kepler, who had given his three laws. Okay, and later on, Newton was able to derive the Kepler's laws from his universal law of gravity. Okay, you can think that Newton's law of gravitation is actually the beginning of all theoretical physics. Okay, so it was the first time anyone had ever written a theoretical expression in mathematical form to predict an outcome, and it was in agreement with some observations. Okay, so we'll look at those observations as well. All right, so no wonder Newton is considered as the greatest scientist who ever lived. Okay, what this Newton's universal law of gravitation is telling us is that there is a gravitational force of attraction that is existing between two objects. Okay, and certainly it is an experimental law, and uh, Newton based his observation of the way the Earth and the Moon are orbiting, and he said that the same kind of relationship that exists between Earth and the Moon, that kind of relationship can exist between any two objects on Earth. Okay, so it is not something that is specifically related to just Earth and the Moon, or another planet or another system. It is a universal law that applies to everybody. Okay, so you can just imagine, during those times there was a huge divide in society over the culture and religion and all these different aspects of how things work. The scientific community was not that well established. Okay, and here comes Newton, and basically he says that there is something that is uniting every person and every object in this universe, and that relationship that is existing between any two individuals or any two objects that are having mass is this universal law of gravitation. Okay, so that was a huge play field where everyone is the same kind of everyone is dealt on the same plane. So that was very objectionable to a lot of people, right? Because so that was the profound impact that Newton had, right, and science had in uniting mankind. Okay, I'm sure you have heard about the apple story, right? That Newton was sitting under the tree and an apple fell, right? And I mean, there are accounts of this, whether it is true or not historically. Okay, later on, many people gave different reasonings as to whether the story was correct or not, and whether they were actually present. But regardless of that, what you need to take away from this picture is that what exactly is going on here, right? So when Newton was supposedly under this tree, right, he saw that this apple fell from the tree. Okay, so what did Newton think of here? All right, so let me ask your interpretation of what is going on. Right, so if you see an apple fall from the tree, what can you interpret?
So, some kind of force acting on it that's like making it move from its position when it breaks off.
ओके ओके गुड गुड और क्या क्या आ रहा है लोगों के दिमाग में बताओ.
सर ये
So,
सवाल आएगा सबसे पहले कि वो नीचे ही क्यों गिर रहा है, ऊपर क्यों नहीं जा रहा है, फिर और किसी डायरेक्शन में क्यों नहीं जा रहा वो, ये सारी ये
Exact,
एप्पल नीचे आ रहा है.
exactly. That is essentially the question Newton asked. Okay, the question he asked was, why is this apple basically falling in this particular direction? Okay, why isn't it going left or right or upwards? Why is it going exactly in this direction? And then he realized, okay, if Earth is curved like this, okay, whatever the curvature of the earth is, I'm just exaggerating, okay, and if the apple is falling, where is it trying to go? And he came to the conclusion that this apple is trying to go to the center of this earth. Okay, so he concluded from this result that, that is where, the entire mass of the object is concentrated, and there is a force of attraction that is causing this apple, wherever it is falling from, all of these objects, because of the gravitational attraction, they are trying to go towards the center of the earth. Okay, so that is one way to look at it. Okay, and later on you will see that Einstein had a different interpretation of what is going on here. Okay, so but with the Newton's interpretation, that is what he was trying to understand as to, where is this apple heading. Okay, like I mentioned, Newton realized that this force that is drawing the apple or whatever object towards itself, this must come from within the earth somewhere. Okay, and then he said that this force is what is actually keeping the moon in its orbit around the earth. Okay, and that is the force that we now call the gravitational force. Okay, if there is earth that is exerting a downward force on you, and you are standing on the earth, then because of the Newton's third law, you can say that you yourself are applying a force on the earth as well. Okay, and of course the force that you are applying is very, very small, it's undetectable, but that is not always the case. Okay, so there are cases where you can detect it as well. Okay, and just by the same reasoning, if you have the moon and the earth, right, and the moon is going around the earth, and there is this gravitational force is acting between them. Okay, so there will be a force that is exerted on the earth by the moon, and there will be a force that will be exerted on the moon by the earth as well. Okay, and this gravitational force that one body exerts on the second body, right, it is equal and opposite to the force exerted by the second body on the first one. Okay, just by using the Newton's third law. Later on, what Newton observed from his calculations was that these orbits of the planets, he concluded that this gravitational force that is exerting, it decreases as the inverse square of the distance r between the two masses. And the relationship is that it depends on the mass, and it's inversely related to the square of the distance between those two objects that you're considering. So if you're considering the force, for example, that is acting on this mass m1, okay, given by this F21. Okay, and by notation what we are saying is this is the force due to the second mass on the first mass. Okay, so there is a second mass m2 here, and because of the presence of this second mass here, it is causing this mass to be attracted towards it, and henceforth there is a force that is acting on this mass m1. Okay, and it depends how much the force F21 is, depends on the distance of separation r between these two masses. Okay, so F21 will be proportional to m1 m2 divided by r square. Okay. Now, like we were discussing, because of the Newton's third law, this force F21 that is acting, similarly, there is a force 1-2 acting on this mass m2 because of this mass m1, because even this mass has this particle has some mass. Okay. So this force now that is making this particle move towards this object here, okay, because that's the force, it is in this direction, so then the acceleration has to be in this direction, right? So this force is being caused on this particle because of the presence of this particle. Okay. And both of them have to be equal and opposite to each other. Okay. And so if f12 is this value, then f21 has to be minus of this value. Okay, just for the sign convention. All right. So again, the direction of the force that is acting has to be along the line that is joining these two masses. Okay. So there will be a single line that is joining these two masses around the center. So that's the direction of the force that is at play here. Okay. So again, so whether you're considering the moon and the earth, or the earth and the sun, any two objects, as long as they have mass, and so then there is essentially a force that is acting between them. Okay. And this proportionality constant, we write it as this capital G. Okay. So this capital G is known as the universal gravitational constant. Okay. And of course we can measure G. Okay. And what we have found is that this G is the same for all the objects. Okay. And it is a very, very small number. Okay. And one way to calculate this constant of proportionality is by using this Cavendish measurement. Okay. So what we do is we have these two masses that is separated by a distance. Okay. And we have a light source that is getting reflected off a mirror. Okay. And it shows us some position here. And then what we do is we bring another mass close to one of these masses. Okay. So if there is a force of attraction, then this mass will get attracted towards this heavier mass, and so this entire pivot will rotate, and what you will see is your light reflection here on the scale will rotate. Okay. And so by that rotation you can actually calculate the value for G. Okay. And this was calculated to a very, very precise value, and we have found that the value for this capital G is 6.67 times 10 to the minus 11. Okay. That is the value, and of course the units will be Newton meter square divided by kilogram square. Okay. And you have to remember that this G is a universal constant. It is applicable for any two masses that are present in this universe. Okay. Force is a vector quantity. Okay. So the correct way of writing the notation for this force is to write as minus G m1 m2 by r square to 1, and then you have this unit vector. So this is the unit vector, remember this with the cap. So we are writing as r21, so that is telling us that it is an attractive force, and it gives us the direction as well where the force is acting. Okay. For now, I have provided you two tables here. Okay. So it has almost all the information that you need to know to perform some of the calculations that will be coming up in your tutorial and some of the examples later on. Okay. So this first table here, it is giving you the values for these planets. So you have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus and Neptune, and we have basically your mean distance from the sun. So it is actually telling you how far this planet is from the sun. So from these values you can actually calculate the gravitational force of attraction between the sun and these planets. Okay. And astronomical unit AU is actually the Earth's mean distance from the sun. Okay. So you can see here that for Earth we have 1 AU as the value. Okay. And values below 1, that means these planets are closer, and values above than 1, then they are away from it. So sometimes it is useful to use the astronomical unit, so that it's easier numbers to work with, right? Or else you have to work with these millions of miles or millions of kilometers type of number, because these distances are of course very, very far away, okay, from each other, right? What you also have is the orbital velocity omega for these planets as they go around the sun. Okay, so that will help you to calculate the time period of revolution and other quantities when we need them. Okay. Similarly, you have the information about the planets themselves, as to we know that just like Earth is rotating about its own axis, the other planets are also doing the same. And so here you see the period of rotation of each of these planets, that they are rotating about their axis. And here you have the diameter of each of these planets. So that essentially tells you the radius of the planet, or the or the entire diameter of the planet. Okay, so and you also have other important things that you can see on the third table. And here you are seeing basically the mass of each of the planet. Okay, and we are also seeing some of the calculations of mean distance from the sun, and this weird quantity t square by r cube, which you will later on see in the course what it means. Okay, so I'm sure you have heard that Pluto was removed from the planetary system in 2006, and now it is known as a dwarf planet. Okay, so now we have only 8 planets that we know of in our solar system. Okay, let's do some quick calculations to get a feel of this gravitational force. Okay, so because it's certainly a question that you might ask me, right? Because if there is gravitational force present between any two objects, and then certainly you can question me as to you have always been in class, you're sitting next to a person, and why haven't you felt this force, okay, between the person sitting right next to you? Okay, so let's take that example, that you have one person of mass 50 kg, and you have a second person of mass 70 kg. Okay, and you are sitting right next to each other on a bench very close to each other. Okay, so what will be this gravitational force of attraction between you two? Okay, and again we can use the formula. We can make a educated guess that let's keep the distance of separation as 1 meter. That's a healthy distance of separation. And then the force will be this value g m1 m2 divided by r square. Okay, and we know g is 6.67 into 10 to the power minus 11, and you can multiply the masses and divide by 1 meter, and so everything is in SI units. So we get the value for force as a value of the order 10 to the power minus 7 newtons. Okay, so there you go. The force is existing, but it is very small to be noticed. Let's take another example of a spacecraft of certain mass. Let's say its mass is 2000 kg, and it is flying at an altitude twice of that of the radius of the Earth. Okay, so in this scenario now, what will be the force that is acting? We're getting roughly around 4900 newtons. Okay, I believe you can now make a realization that all the satellites and all these objects that are doing circular motion, right, since they are doing this circular motion, they have to have different velocities, because the velocity vector is changing. So there is a force acting, and the force that is acting is your gravitational force that is making these objects go in this specified orbit around the Earth. Okay, so let's do another interesting example. And here now we will calculate the force that is acting on the moon, but not just because of the Earth. We will now take the sun as well into the picture. Okay, so now we have two objects. Okay, now both of them are exerting the forces. Okay, so let's say that the force of attraction between the moon and the sun is this value f m of s. Okay, and the force of attraction between moon and Earth is this f m of e. Okay, you can assume that they are at right angles to each other, and we have been provided the values for the mass of the Earth. Okay, we have been provided the value for mass of the sun. okay, which is 2 times 10 to the 30 kilograms, and you have the mass of the moon, which is 7.35 into 10 to the power 22 kilograms. Okay. Uh, Also, the distance of separation is provided between the moon and the earth, and moon and the sun. Okay. So in this case, the net force that will be acting because of these two forces will be pointing in certain direction here. Okay. And we can assume that this force that is shown here, okay, which is this value f, okay, here, which is the same f here, is just the sum of f of mfs plus f of m of e, which is this value. Okay. Because this force is exactly the same as this force. Okay. The value that you will get for the force between the moon and the earth will be roughly about 2 times 10 to the 20 newtons. Okay. And the value that you will get for the force between the moon and the sun will be 4.34 into 10 to the power 20 newtons. Okay. And of course, you have to be careful if you're calculating the magnitude of this f, it has to be the square root of the square of the magnitudes of these forces. Okay. Remember, this was just the vector sum of the two forces, right? So if I have to calculate the magnitude, right, the magnitude, I will have to do the square root times the square of the individual magnitudes. Okay. And if you do that, you will get a value of about 4.8 times 10 to the power 20 newtons. Okay. And interestingly, what you can do is you can calculate tan of theta, and tan of theta will be your opposite side by the adjacent side. So you will have this force of me divided by force of ms, and if you do that, you will get a value of 24.6 degrees. So that gives you a rough angle of where the moon is headed with respect to the earth, or with respect to the sun, wherever frame of reference you are trying to observe the movement. Okay. So that was one of the examples, okay, where you don't have just one forces, but you have two forces because of two objects in the vicinity of the moon, which is where we are considering the force is acting on the moon. Okay. So like we were discussing before, you can have a scenario when you have many particles that are influencing a certain particle. Force that is acting on the particle one would be this uh, vector sum of all the individual forces that are acting on this one because of the particles 2, 3, 4, and so forth. As long as you have n particles, so you can add all of them up. Okay. And certainly this is an gross approximation, and the reason why we use it is because it works. Okay. If you do the calculations, if you do experiments, you get the result that this law is valid. Okay. So that's how we calculate the case where you have a one object that you are trying to investigate, and then there are many particles around it that are exerting attractive forces on this object. Okay. And just like I had shown before, you can find the resultant angle as well by just looking at the vector sum of these forces. So you get the direction and the magnitude. Okay. So interestingly, like we were discussing before, right, when Newton was questioning the idea of where the apple is going when it is falling from this tree, right, and we realize now that for a spherically symmetric mass distribution, okay, the if there is a uniform density of this mass distribution, okay, and for such kind of system, what happens is that there is a specific place which is at the center of this mass distribution, as if the entire mass is concentrated at that position. Okay. So the entire earth you can just consider as a point particle with all the mass that is concentrated at the center of the earth. Okay. So that was the reasoning of where the object is going, because it's going towards the center of the earth, because this earth is a spherically symmetric mass that is distributed to a good approximation. Okay. And in such scenarios, a person or any particle of mass m that is at the earth's surface, okay, it will feel a force of gravity of g times the mass of the particle times the mass of the earth, right? Because you have a situation where you are essentially let me draw it out. This is the earth, right? And somebody is standing here. So relative to the center, this is the radius of the earth, okay? And that is the value that you have to use here, okay? That this small r is essentially the radius of the earth, okay? Let me use small r here, okay, just for consistency, okay? So small re is the radius of the earth. That is the radius of separation between a person that is standing at the earth's surface, okay, and that needs to be plugged into this equation to calculate the force of gravity that is acting on that mass or on that person that is standing at the surface of the earth, okay. And this applies to a spherical shell as well, okay. So both of these cases we'll solve later and see how they hold together, okay. Is known as the gravitational acceleration, okay, and the capital G is known as the universal gravitational constant, okay. So you have to not confuse between the two. You should know exactly what is the difference between this capital G and the small g, okay. So we already defined that this capital G is universal for the all the objects, okay, irrespective of where they are in the universe. This capital G is a constant value. Its value is 6.673 times 10 to the power minus 11 with its units, okay. But this small g, which we know as acceleration due to gravity, which you might be familiar with the value 9.8 meters per second square, this value is an approximate value of acceleration at the earth's surface, okay. So in the expression that you have, okay, of your gravitational force, we always use the gravitational force as mg, right? This g essentially is this product of capital G times the mass of the earth divided by the radius of the earth, okay. So that is what is happening here. The force of gravity acting on an object on the surface of the earth will be this capital G times whatever mass that object has, times this mass of the earth divided by radius of the earth square. So this entire term g m of e divided by re square, this, when you calculate this out, you will get the value of g. So if you plug in the value for this capital G, right, and you calculate, you plug in the value for mass of the earth, which is 6 times 10 to the power 24, okay, and you plug in the value for the radius of the earth, which we know, okay. uh, so if you plug in those values, you can calculate the value of g, okay. So similarly, if you know this value of g at a certain location, right, then you can calculate the mass of the earth, okay. So either ways is fine, okay. So again, what you have to realize is that this value of g is an approximate value, okay. So we are using the value of separation as the radius of the earth. So this value is valid only at the surface of the earth, okay. So if there is a position that is at a certain height from the surface of the earth, then this term here should have the radius of the earth plus this h term, and then you have to square it, okay. So that needs to go into the picture as well, okay. So certainly if you look at the example that what is the value of g on Mount Everest, it will not be the same value of g that you're seeing in Roorkee, okay. So these are some estimate of the values, okay. So if you are in altitude, okay, at 1000 kilometers, okay, so the value of g that you will experience is 7.33, okay. And suppose you are at a value of 2000 kilometers, okay, you can see that the value of g is going down. It's 5.68, and all the way if you're up to 2000 sorry 10,000, then the value of g, the small g, is only 1.49, okay. And certainly by convention, what we say is if you are at infinity, then you're so far away that you're not feeling any force of gravity at all, and so then this g value is essentially zero, okay, because this r that we are using in the denominator, it's so big that the value of force and the value of g is very small, okay. So let me summarize in the end, okay. So what you need to always remember is that gravity is and attractive force. Okay, very important to remember. Okay, it was revolutionary. Why? As you can see, it is applicable to any two objects in this universe. Gravitational force essentially is universal, is acting on any two objects in the universe. Okay, and from that you get that G is a constant term. Okay, and the value is 6.67 into 10 to the power minus 11, and like we said, it is Newton meter square plus kilogram square. Okay, very important. This is the capital G. And then we also talked at the small g, okay, which is at the surface of the earth is about 9.80 meter per second square at the surface of the earth, and they are not the same. Okay, and you see, gravity is a very important force because it is controlling how the universe is evolving. Okay, so the entire evolution of the universe, is basically governed by the gravitational force. We don't think about it too much, in everyday life, but it is governing how the universe itself is evolving. They come into picture only when you have objects of very large size in question, but nevertheless it's a very important force. Okay, and the other thing that you have to remember is that uh, the case where you have some spherically symmetric objects or some objects of certain shape, then certainly the gravitational field and the gravitational force they will create is of a very peculiar kind. And so later on in the next few lectures, just like we calculated moment of inertia coming from a cylinder or from a sphere, we have to figure out the gravitational field that is coming from a sphere, the gravitational field that is coming from a cylinder, and then we can apply that field to an object, and we can see how the object will move when we keep it in this field. So we were looking at the free fall drop of this two objects when they were entirely in vacuum. Okay,